Thank you very much. So, various people have asked me, have I ever been here before? And I can safely say to almost all of them, yes, I was here before you. And that's because, maybe I was here in January of 2007. And it was a program on that day. So this is the opening colloquium of the Hausdorff Center, the first event, starting with Felixato and then a bunch of scientific lectures. And that's when they started this tradition that I speak last. And, we're following this today too. It's the second occasion on that. Anyway, it is wonderful to come here and see what a fantastic place this has grown into, and to enjoy it myself. It's a great research environment. So thank you. So let's get rid of that. Okay, I think we're done. So this wave localization, you notice I don't usually do this, have a giant logo saying whatever my funding is coming from, but I wanted to explain a little bit the Simon's collaboration of localization of waves because it's different than anything I've done before. It's a different structure than most large grants, and it's really affected the research, as you'll see. So it's a very interdisciplinary group of people who got together and wrote this grant to the Simons Foundation. So there's 10 of us at a time. It's international in that there are several people from France, Mayer and Weisbuch and Aspect and Philoche. Friend is from Cambridge in UK. Then Jim Speck is from California, David Jerrison's from MIT. Svetlana May-Baroda is our leader in all this. She's the director of the whole thing and really the one who got it going. And so it's been great to work. And then the other thing is it's very spread out in what people do: geometric measure theory, atomic physics, semiconductor physics, Fourier analysis, and so forth. And I'm the computational guy in the group. And there were some connections between these people in advance, but not too many. Probably everybody had worked with one or two of the other people and didn't know all of the others. In some areas I didn't know people, I'm ashamed to say, because they're really at the top of their field, but it's not my field. Ugo Dumino-Copin won the Fields Medal earlier this year, so we definitely made a good choice with him. We're very proud of him, and he was sort of the leader of the pack, but now it's a little bit of a shadow because Alan Aspect won the Nobel Prize in Physics in the same year. So it's a very good group of people, and I love learning something new by talking to people who are really expert in it, and there's been a lot of that. And what do we do? So this is a grant. We got it for 4 years, extended it to the maximum of 7. It's $2 million a year, so there's a lot of money floating around. And what is it for? Well, we're all building groups, and the groups are all interacting to make one big group. That's our group at this point. So there's Svetlana and the PIs on the top row. These are our consultants, Shuji Nakamura, which I'll mention a little bit later. Jill Pfeiffer, you probably know, is a great analyst, and Terry Tao, there's no question that you know. And then these are sort of associated scientists, relatively senior people who are working with us, and then postdocs that we've gotten with the grant money, and graduate students, and alumni graduate students who have a job now. So it's been a fantastic group, and I can honestly say I know not all of these people, but most all of them. Because what do we use the money for? Well, of course, we pay their salaries, but we also travel a hell of a lot and visit each other and have conferences and meetings. And that's how how we get to know each other. And of course, there's been lots of Zooming, as you can imagine. Okay, that's the end of that story. And I want to talk about the Schrödinger equation and localization. And I'm not assuming that you know much about either of those things. I didn't when I started. So the Schrödinger equation was published in 1926 by Schrödinger. It wasn't derived, because you can't derive it from classical physics. It came into his head, and it was explored, basically. And that's it. I, the square root of negative 1, h bar, tiny constant. Time derivative is equal to minus h bar squared over twice the mass of a particle times the Laplacian, plus potential energy term, which is just a coefficient, times the function. And that's the time-dependent Schrödinger equation. And that describes this function psi. It's an initial value problem, maybe boundary value problem, initial boundary. So psi is the wave function at any time, which tells you what you can observe about that particle. The most famous thing is that this psi can be complex, since we have an I in there. The most important thing is the complex modulus squared of psi is the probability density of finding the particle psi at any point. But there's many other things you can do with psi. The spatial operator on the right-hand side is called the Hamiltonian. Here it is. And if you look at this, well, if somebody asked you to solve that, you'd say, hey, that's linear, and the coefficients don't depend on t. This is separation of variables. And if you do separation of variables, it means you want to find the eigenvalues and eigenvectors of the Hamiltonian, and then expand everything in terms of the eigenvectors. So instead of solving this, you could solve this. Just the eigenvalue problem for the Hamiltonian with some sort of normalization. That's called the time-independent Schrödinger equation. And I mean, it sounds great, and if you can get those eigenvalues analytically, it is great. So for instance, for a particle in a harmonic in a parabolic well, which creates a harmonic oscillator, we can write down the eigenfunctions and eigenvalues, and so you can also write down the solution to the transport equation. So there it is. Now I've become a mathematician and set h bar and 2m equal to 1. It's fun to see what happens to the physicists when you do that and how they explain it. Never mind. Let's take an example of this. So first I'll take the example where v is 0 and h is just the Laplacian, or maybe v is a constant. That's basically the same thing. And let's put it on a square with, say, periodic boundary conditions, so boundaries don't get in the way. Then what are the eigenvalues of the Laplacian? Well, constant is the fundamental solution, is zero energy. And after that, you have trigonometric polynomials, cos of 25x and sine of 13x plus 5y and so forth. So this is the first mode, and that's one of the high modes, 57th. Then I'll do the same thing for this potential, which is some smoothly varying function between 0 and 200 or something like that. And then the fundamental mode is no longer constant. It varies a little bit to take into account the coefficient. And the 57th mode is not exactly trigonometric, but it looks a lot like a trigonometric function. It spans out. And then we take that potential. So the only change is v is now that. What is that? I took the square, I broke it up into 80 by 80 subsquares, and I assigned a random number between 0 and 128,000. Okay? And then those are the first eigenvalue and the 57th eigenvalue. And all the ones in between look something like that. So this localization is not some small effect. This is some really first order effect. Changes the nature of, well, I gave a summary here. That's the takeaway message. Disorder changes things greatly. So that's the phenomenon we want to look into. Why do we care about it? I'll give a real application at the end, actually, from the same guy's group. This is one of our PIs, Jim Speck, who has a laboratory at UCSB with this atomic probe tomography machine on it. That can take a tiny sample and analyze it atom by atom and tell you where the atoms are and what kind of atoms they are. It's unbelievable to me, except that I've seen them so many times now. I expect to believe them. So these different colors, this is indium gallium nitride. So those different colors are indium, gallium nitride, and then various impurities, phosphorus, and so forth shown here. And this is an LED device, and these stripes are quantum wells that they built into it. They build this to look like that. But of course, what they build it to look like is step functions, and it's not step functions. There's a whole lot of disorder in there in the middle. And you might say, well, just ignore the disorder. It's basically a step function. But we saw you don't go ignoring disorder. Disorder changes everything. So let's go the other way. So the person whose name comes to mind when you tell a physicist, a condensed matter physicist, about localization, they say, oh, you mean Anderson localization. Actually, literally, Anderson is the guy who invented the term condensed matter. So he's very well respected in that community, of course. And what he said is, well, electrons move through metallic substances, and that's how we get electric conductivity. But if there's impurities in there, they'll scatter the electrons, and we won't conduct electricity as well. And then he determined through experiment and then through theoretical considerations that if you have a certain level of disorder, all of a sudden conductivity drops down to 0. It doesn't go slowly towards 0 at infinity. It stops at some point. It's a quantum effect, obviously. And he got the Nobel Prize for that in 1977. The paper was in 1958. I wrote down what he did mathematically, but I don't think it's too important, but there is the exact, he looked at actually the random potentials that I showed you pictures of, break the square into many subsquares and assign random numbers. He didn't use the Laplacian, he used the 5-point difference Laplacian and 7-point difference Laplacian. But the main thing, he showed that there's a critical value after which you have this conductor insulator transition. By the way, defining localization isn't really so easy. Even though you saw it, it was very obvious. Those functions were not 0 off this main thing, because the solution of an elliptic equation is never 0 everywhere on a set of positive, on a open set. They're just exponentially small, which is meaningful if you're on the whole plane. What do you mean exponentially small? If it reaches the boundary and then it stops. So it's a little tricky. So in some ways, localization is, I know when I see it, you have to be very careful you want to make it rigorous.
There's an implicit length scale when you have an exponential decay. So in some sense, there's maybe a range of length scales for each of these structures, a family of length scales over which that decay occurs.
Well, I mean, if you take, for example, let's not get into it. I don't disagree with you, but it's tricky to make it rigorous. It can be done in different contexts. So one thing is Anderson localization. Believe it or not, it's still not really fully understood. There are many questions about it. Here's some relatively recent statements about it. So electron localization is what we're talking about. That's the particle that Anderson was looking at. And unfortunately, electron localization is devilishly hard to confirm. Experimental observations are sparse and covered with disputes and controversies. And then here's an example. They try to compute various critical parameters. These are supposed to be important numbers to physics. They're very interested in what they are. Most theoretical result, like 789, predicts mu equals 1. But there's another prediction of mu equals 1/2, and numerical simulation gives mu equals 2/3. So it's a bit of a mess. And this goes back to Anderson's Nobel Prize lecture. He said very few people believed in localization at the time, and even fewer saw its importance. Among those who failed to fully understand it at first was certainly its author. It has yet to receive adequate mathematical treatment, and one has to resort to the indignity of numerical simulations to settle even the simplest questions about it. So my goal in life is to get rid of the word indignity and convince you that actually these numerical simulations are beautiful, elegant, and illuminating. Okay, so this is the new ingredient I'm going to talk about, and it's not so new anymore. This is 10 years old. The landscape function is one of the reasons this group of people gathered to look at this. So I need to tell you what is that. Well, first, if you have never done quantum mechanics, you need some sort of examples to have some feeling about what's going on. And the simplest non-trivial example is the finite well. So let's say we have one-dimensional, we're on the real line, and the potential is just a well like that. with walls of height v and normalized radius of 1. So if you have a wave coming by with energy lower than the height of the walls v, what will happen, well, if it were a classical wave, if it didn't have energy v to get out of the well, it would be confined to the well. With quantum mechanics, you get this by solving the Schrödinger equation. What you'll get is something that's mostly confined to the well, but diagonally outside the well. And this is easy enough because if you write down the Schrödinger equation, minus u double prime plus vu equals lambda u, on that thing you can solve it by hand. And what you see is the higher the wall, the more it's confined. And when the wall height goes to infinity, then you just get a sine wave confined to the boxes, the ground state. Now, what about if you have a more complicated potential? Well, one of the first things people said, well, is if it has wells, and then maybe some other stuff, probably it still localizes to the wells to some extent. So Agman was the one who found the mathematical tools to deal with that. And so he considered there were smooth potentials defined on all of Rn, no boundary conditions. And he viewing the Schrödinger operator as a closed operator in L2. And he defined what's called the Agman distance by taking the metric of the plane, or of Rn, and multiplying it by a conformal factor, which was the amount by which the potential is higher than the energy of the mode you're looking at, higher than an eigenvalue. So for every number lambda, you can look at v minus lambda, but cut it off at 0. When v goes below lambda, it's just 0. And you multiply that factor times a length when you measure the length. So here, if we take a path gamma of s going through, connecting 2 points of the plane, gamma dot of s, absolute value is its velocity. You integrate it, it's the length of that path. And if you take the smallest length of all possible paths, that's the distance between them in this weighted metric, right? So that's a distance that counts things as much further if v is high there, and if you're in a low potential area, it counts things as less or even 0 to walk in them. So Agman proved that if you have an eigenvalue of the Hamiltonian with eigenfunction c, and you have a regular v, which is above lambda outside a compact set, so on most of the, only on a finite compact set, are there areas where the distance goes down to 0. Then he said, you can take any number alpha less than 1, so you can almost take 1.999. There exists a c such that the integral of e to the 0.999, the distance from x to some fixed point, like the origin, that exponential weighting factor, which is essentially e to the distance of x to 0, times c, makes this thing integrable. That integral finite, and since this is exponentially growing with the Agman distance, that's another way of saying c is exponentially decaying with Agman distance. So he proved it exponentially decayed with Agman distance, as long as the Agman distance was positive, not when it gets down to 0, and under these assumptions. And that's sort of the best result for understanding decay of Schrödinger eigenfunctions, theoretically. Well, of course, it's extended in many small ways, but that's a dual. But the potentials we consider don't fit in with this theory. They're not continuous, they're not smooth, they're discontinuous, piecewise constants mostly. I'm on a bounded domain, so there's that. But the most important is they don't have wells stuck inside a compact set. So here's another potential I like a lot. I'll call the first one we had the Anderson potential. This is the Bernoulli potential, where the numbers are not uniformly distributed between two points. They're either 0 or 1, or 0 or something, 0 or 4 in this case. So let's take this as our potential. It's 70% 0, that's white, and 30% 4. If you know percolation theory, you know that's above the percolation limit, which means that it's with high probability possible to get from a white point on this side to a white point on the other side sticking inside white. So there's no well. If you're in white, you can go anywhere. And I've shown that in the picture. That's the connected component of white stuff. Almost all the white stuff is connected, and it goes everywhere. So the Agman distance between any two of those pink points is 0, and that Agman's theorem doesn't say anything, even if it did apply. So you look at the eigenfunctions and say, okay, maybe they don't localize, they spread out everywhere. No, they don't. You don't seem to see much of a difference. Those are some of the eigenvalues of the Bernoulli operator. So now what's this landscape theory that I say was a breakthrough? That was done by two of the PIs in our project. Svetlana Beveroda, who's directing it, and Marcel Fluloge, who's a condensed matter physicist from Paris, now the Landrivan Institute, who together they came up with this because I think he was attending a lecture of hers and they started to talk. So take any elliptic operator, it doesn't have to be the Laplacian. Then the landscape function is HU equals 1. So it's a really simple thing. And as opposed to the Schrödinger equation, you just change the lambda u on the right-hand side to 1. Simplest thing you can think of other than 0. Now, take an eigen pair of that Hamiltonian, H sigma equal, H sigma is equal to lambda sigma, and normalize sigma to be L infinity norm 1, not L2 norm 1. Then you can prove this bound always holds. Sigma of x is less than lambda times u of x. So the solution to this equation will always be an upper bound for the eigenvalues, all the eigenvalues, if you normalize them in that way. And if you put the eigenvector here, there's a constant which is the eigenvalue. That's really easy to prove. You could all probably prove it given a little time, and if you were given a hint, you'd definitely prove it, and the hint is maximum principle. Use the maximum principle, and this comes almost immediately. And so it applies to any operator H that satisfies the maximum principle. So I like to see things much more than to read theorems like that, although my profession makes it necessary. Let's do a 1D example. The domain is the interval from 0 to 64, and I've cut it into 64 pieces and assigned a random number between 0 and 8 as the potential, piecewise constant. Solve HU equals 1. Well, in 1D that's really easy. And this is what you get. You notice, let's see, here, where the potential is high, corresponds to here, where the landscape function is low. That's not surprising because, remember, it's Laplacian u plus VU, so if V is big, U has to be small, till the Laplacian term hits over. Okay, now what I've done here is I've taken the first 4 eigenfunctions of the Laplacian, of the Schrödinger operator with that potential, and I've scaled them by 1 over lambda. So I've taken this lambda and I've put 1 over lambda in front of the eigenvalue. So the smaller lambda is the higher the eigenvalue. So this is the fundamental mode, and this is the second, this is the third, this is the fourth. And indeed, they all are bounded by the landscape function. So the landscape function had something to say about all the eigenfunctions. So I don't want to spend too much time on the original argument of Fluloge and Rhoda, but if you look at their paper in PNAS, what they basically say is, what they basically say, if you look at it over here, suppose you're on this eigenfunction. Well, the landscape function dips down, and it has to be below it, so it has to dip down too. So it has to be almost 0. That's really not very true. It's not so close to 0. But so this sort of pushes it down to 0, and in that case, then it's a Dirichlet eigenvalue of the region where it's 0. So if you sort of cut it off there, it's almost a Dirichlet eigenfunction. Now, on the complementary domain, the rest of the domain, it's also 0 here and here. So it's a Dirichlet eigenfunction of the complement too, taking into account the boundary in the right way. But it's very unlikely that there'd even be an eigenvalue shared by both. So it'll be 0 on one of them and non-zero on the other. And that was sort of their explanation of localization. And this picture came from their paper. These are ridges. I'll show you later how they make them, but you compute the landscape function in higher dimensions, and you look at the mountain passes and ridges separating them. And they're here, and these are the eigenfunctions, and they do seem to follow the ridges pretty well, very well. Okay, I'm going to also skip this example because we're not having a lot of time, and get to when I started working on this with them. I heard a lecture by Marcel after Svetlana brought him to Minnesota, and that's when I got interested. And I said, you know, I can show you some of this in computations, and they were very excited. So we started to work, and we turned out there's a better way to view the landscape function than through that maximal principal inequality we had before. Instead, we have the following construction. Take the original Hamiltonian minus Laplacian plus v and conjugate it by u, meaning that you take a function, multiply it by u, then apply the Hamiltonian, and then divide by u. Whenever you conjugate, you don't change the eigenvalues, and you change the eigenvectors in a very predictable way. Now it turns out, if u is the landscape function, hu equals 1, then you can rewrite this. It takes a little work, but you can rewrite it so it also brings up into a sum of a second order term and a zero order term. The second order term is not Laplacian anymore. It's L, where L is given here. It's div u squared grad phi, with this positive u squared here, divided by u squared. And W is no longer just this piecewise constant potential or any potential. W is 1 over the landscape function. So we say W is an effective potential. We have an effect in our Hamiltonian, we have a potential W, which is not the real potential because that's not the real Laplacian, but an effective potential. And what's it for? Well, it's smoother than the true potential because we got it by solving the second order elliptic equation. It's almost C2. It often is confining. So if we go back, if we go back to this picture of Bernoulli potential, that's not confining. There are no wells, as we talked about. The pink spreads everywhere. But now if we go to the effective potential, well, this is it actually. This is the effective potential for that exact Bernoulli potential. And this is the same picture as that. It's just a different way to show it. So for instance, here is a deep area. The blue is low. There, the potential is low, but it's surrounded by green, which is not so low. That's what we're seeing here. The blue is low, and it's surrounded by the stuff that's not as low. So that's a confining well. You could imagine a wave getting stuck in there. Well, it's hard to imagine where it would get stuck in the other one. So that's what I mean when I say W is often confining when V is not. W accounts for more of the energy. We've just done specific cases of potentials. And you may have a situation where 95% of the energy comes from the Laplacian term and 5% from the potential term. But once you solve this, it'll be more like the opposite. It'll be more like 90% in the potential term. That's fairly common. And what we decided to try, and what worked eventually, was we tried to use Agman theory with Agman distances, but instead of the Agman distance with the true discontinuous nasty potential, we use the Agman distance with the effective potential. And this is mostly because it's cool and it helped us get the grant, but that's a picture of the effective potential in 3 dimensions. So what you see is there are deep wells like that purple one surrounded by green. That's where you're going to get eigenvalues. Okay, there is some theory to this, but not very much. So we proved this theorem, and I don't think I want to go through it completely. What it says, again, is that if you have an area where you look at an area where W is larger than some lambda, and now you take the distance to the boundary of that region, as using W, the effective potential to compute the acting distance, exponentiate that, then you'll get a finite integral with C there, meaning C has to die exponentially in such an area. So let me just show you. So here's an example of that. Here I've taken, is this the, yeah, no, this is a Bernoulli potential. I think it's the one. Let's see, is that this one? Just look over here. I think that's the same potential. So what I'm just showing you, the ridge lines here projected in, and the first eigenfunction, yeah, it goes there in that blue C we saw at the bottom. And it decays exponentially as it moves away, because what that theorem said is if you climb one of those walls, there'll be an exponential decay while you cross the wall. But then we said, well, it applies to all the walls, not only the wall right next to the peak of the eigenfunction. As this eigenfunction goes from that point over to here, every time it crosses a wall, it decays exponentially. So that means all the area where it looks like it's zero has lots of structure. So I wanted to see that, so I plotted that. So this is a plot of the log of that. And what you see is it starts out one here by normalization. And then every time it crosses a wall, it goes from dark brown to red-orange, to orange, to yellow, to green. It drops down by an order of magnitude, more or less. And that happens way over to 13 orders of magnitude. So this structure in the eigenfunctions was completely unknown. Everybody thought they were a spike, and then essentially nothing was happening. Okay, and that brings me to the point of view I want to take in the rest of the talk, which I'm seeing this landscape function sort of has predictive powers. It can tell you that the eigenfunction will pop up over here where there's a C in the effective potential. So the idea is if I give, well, we'll do that game in a minute. So why don't I try to use it as a numerical method? Calculating eigenvectors and eigenvalues, especially a lot of them, is very, very hard. And so maybe you can replace a lot of that calculation with the landscape function. So I thought of a game that sort of captures this, and this certainly helped us with the grant because I asked Jim Simons, who was in the audience, to play. That woke him up, first of all, and that either could have killed us or made the grant, but I think he liked it. Anyway, here's the game. You get to play yourself. So the domain is 0 to 256. The potential is one of these Anderson potentials made of random numbers evenly distributed 0 to 4 IID. And the question is, where does the first eigenvalue pop up? Jim?
So around 100 looks obvious, but maybe
100?
The lowest point.
This point. Yeah. That's the deepest well. So that's a guess. Anybody want to second it or go with something else? Okay, the way I think about it is the wave is thinking like Stephen, saying I want to be in a deep well, but that's so thin I can hardly see it. I won't fit in that deep well unless I have a very high frequency, in which case I have high energy. Maybe it's not deep enough to contain me. So maybe some of these wells that are a little bit fatter, but still pretty low are good. But I don't know, the trade-off in that, it's hard to pick. So our claim is that the landscape theory, the effective potential, sees the potential. That's what the wave sees. It looks at something like the effective potential. So let's compute the effective potential. I solve HU equals 1. That's very easy for me in one dimension. And I have already taken the reciprocal of the answer, and so that's the blue line. And to remind you, I put the old potential back there. And here we see Steve's guess, the deepest one, but it didn't think it, to the wave point of view, it's not so deep because it's so thin, I guess. Well, here it's thicker a little bit, and so this was not quite as deep, but it went down about the same as this one, but this one went even more, combining the two. And so what we do is we just look for the global minimum among all these local minima. And actually the first global minimum, the second, third, and fourth are there. So you get third place prize. First time player. And so now I say, okay, this is where my landscape theory, my effective potential, tells me the eigenvalues will localize. They'll pop up here. How local will they be? So then I have a recipe. You go this height, an extra 50% or so, that's a fudge factor, and take the sub-level set. So that would be about this thick. So I get these rectangles if I apply that rule. And so that's my prediction. The yellow points tell us where the peak of the eigenfunction will be. The green rectangles tell us about how fat the eigenfunction will be, how localized. And then I compute the eigenvalues exactly, which is not hard in one dimension, especially if there's only a few of them. And that gets me these things, and you see it's a pretty damn good match. It's an amazingly good match up here, a fraction of a percent, 0.05% or so. And the shape of these things, well, that's hard to measure, but we'll see. We're getting more in the 2 to 5% range. Okay, second round. Now you know the game. Where do you think it? How does this one compare to the last one? Stephen, you want this point?
I'm not playing anymore.
You want this point? See, this is a trick question. This is the exact same picture as I showed you before. But it's not the same axes. It goes to 256. The last one was much lower. Well, that changes everything. This is a very, solving the elliptic PDE HU equals 1 is very nonlinear process. And so by multiplying the potential by 64 or whatever it was, I've changed the effective potential entirely. It's much more wiggly and so forth. And local minimum are in completely different places.
I should have played twice.
Yours is a winner now. Would you like the color behind? And then I do my trick with the sub-level sets, which now are much thinner because these are much steeper. And that's my prediction, and that's ground truth. So at this point, you should be saying, well, there must be something to this localization theory. It's not just chance that that happened. And now here's a 2D example with that Bernoulli potential I showed you before. And the C that we saw before, the effective potential we saw before with wells in dark blue and peaks in green and yellow. And those are the 4 local minimum and the sub-level sets around them. And now I can compute the exact eigenvalues and see how predictive this was. So there's my prediction, and there's the exact eigenvalues. So there's a lot of, it works also in a complicated problem in 2 dimensions. Here's Anderson potential. That's the one I showed you on the first slide. That's the effective potential. It looks very different, but it has wells and walls, and that's when this theory applies. That's the prediction, and there's a bit of a problem because 2 of the local minimum are right next to each other. And that created some problems. This was my prediction, but there was only one eigenvalue there for those 2 local minimum. It's just a little wave. So this is not going to be a perfect theory where you're going to be able to prove that there's an exact correspondence between the local minimum. But there's certainly a lot of correlation there. Okay, so let's go further. I've talked now about how you could predict the position and the width of the eigenfunctions. What about the shape of the eigenfunctions? Well, now we go to the eigendistance and said, let's use that theoretical tool of eigendistance. And that said the eigenvalue behaves like e to the minus eigendistance. And let's see, and let's just compute that. E to the minus eigendistance is not hard to compute. I thought it would be, because eigendistance is a minimum over infinitely many tests and so forth. But it fits perfectly in the theory of fast marching methods, which comes down to solving like Arnold equations. I won't go into how you do it, but you can do it. And this is what happens. This is the fundamental mode of that 80 by 80 Bernoulli potential. By the way, the thing in the back here, the little bump, is because this is periodic, so that's part of the same thing. This is what you get by taking the eigendistance using the effective potential and just taking e to the minus that, or the reciprocal of e, the exponential of that. And these things look very similar, I would say. But not super similar. If you're a little bit critical, you see that there's more structure in here than in here. This one is a little thinner than this one. So it depends very much on what your norm is, whether that's a 10% error or a 2% error. It ain't perfect, but it certainly has a lot of predictability. If you look on a logarithmic scale, so now I took the log of the first eigenfunction and the log of my prediction, which is just, since it was e to the negative x, take the log of e to the minus eigendistance, I just get the minus eigendistance. And you see these things, this is in a scale of powers of e, not powers of 10. So that's about 10 to the minus 10 on the bottom. And you see all the way out to when the function is 10 to the minus 10, there's still quite a bit of similarity between these. So again, there's the landscape function has a lot of information about the eigenvalues, including their shape to great accuracy, all the way out to when they're very, 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 very flat. And not only for one eigenvalue, for many eigenvalues, although not all of them. You could do the same thing with the second eigenfunction, and again, you see that it has the right sort of shape, basically the right sort of size, but not the detailed structure has been sort of smoothed out. Third eigenfunction, fourth eigenfunction, fifth eigenfunction, sixth eigenfunction. Now this one is interesting. These other ones all appear to be positive, non-negative. They're not non-negative because they're orthogonal to the first eigenfunction, and two non-negative functions can't be orthogonal, but they're exponential. The negative part is exponentially small. But when we got to this eigenvalue, the negative part is not exponentially small. What we have is basically you take that well and you look not at the fundamental mode of the well, but the second mode of the well, which is like a sine 2x instead of a sine x. And that's what accounts for this. And I can't capture that as e to the minus eigendistance, because e to the minus anything is a positive thing. That was a bound on the absolute value, not necessarily the function. This is an open problem. I don't know really how to get this shape from what we know. I'll mention one thing, but hopefully somebody will get better.
Is this the place where the two minimum are quite close, or is it a different one?
What is it?
Is it the place where the two minimum are very close together, like in one of your earlier?
Does it apply when there are two minima together? Well, in this case, I'm not really using that minima structure so much in this case. In that case, I was trying to sort of order the eigenvalues. I don't know exactly the answer to the question. It might again be hard to even make the question precise, but we can talk about it. So we've seen enough of these. But I'm going backwards, so I thought we could see. Here's one thing we can do. Oh, this was another example of something gone wrong. Here we're completely wrong. The eigenvalue is on the bottom edge, and it predicts it there. What happens, this is an area where they get out of order. This matches another eigenvalue nearby with a very similar eigenvalue, another eigenvector nearby with a similar eigenvalue. And then, so this is one thing you can do. If you're a numerical analyst, you usually think a good initial guess is worth its weight in gold. It's very hard to solve, say, a nonlinear equation using Newton's method if you don't know a good place to start. But if you know a good place to start, Newton's method is fast as hell. The same statement for eigenvalues of Hermitian operators is Raleigh quotient iteration. It's fast as hell. It's even faster than Newton's method. It's cubic convergence. And it's not very expensive to implement, but it only works if you're near enough to the eigenvalue. And so I won't go through this algorithm, but what it says is take the initial guess that you get out of this e to the minus Agnon distance and improve it by doing 1 or 2 or 3 iterations of Raleigh quotient. And here's what you get. Say with that one we saw with the first eigenvalue looked like, should be this, that's the exact eigenfunction. And this structure here was somewhat lost here or smoothed out. 1 iteration of Raleigh quotient puts it back, so it's hard to see any difference. And 2 iterations, I say it's absolutely impossible to see any difference. It's pixel perfect. Okay, that's eigenvectors. Eigenvalues, how do you predict the eigenvalues? Well, let me show you again on an argument why the landscape, the effective potential, has more information in it than just the regular potential. Suppose you're trying to get a lower bound on the smallest eigenvalue of an elliptic operator. Well, you're all mostly PDE people, you'll all do the same thing. Minus Laplacian sigma c plus v c equals lambda c, multiplied by c, integrate the Laplacian by parts, and you get the integral of grad c squared plus vcc and that's of course equal to lambda times the integral of c squared. But if you just throw away the grad c term, since it's positive, you get vcc, which is greater than the infimum of v if c is normalized to 1. So that tells you that the lowest eigenvalue is bigger than the infimum of the potential. That's a pretty useless bound, say, for this potential here, or the potential that Stephen was picking, because one of the things when the infimum went down essentially to 0, and you didn't learn anything new, that the eigenvalue is non-negative. But the effective potential is much more moderate in its swings, and then you get a good bound. In fact, this is the lowest eigenvalue, the red level, and it is pretty close to the infimum of the effective. And the same argument shows that that's the real lower value, the real lower value. So how are we going to compute the eigenvalues? Well, this is a terrible argument here, a terrible heuristic argument. I should be embarrassed to show it, but it's the first thing we use, and it works pretty well. The idea is that if we look at these eigenvectors, like the red one or the blue one, they look sort of like bumps. So we define a bump to be a paraboloid cut off by the plane like this. Okay? They don't really look all that much like bumps, but they don't really look quadratic because of the way they're not convex at the bottom. But we assumed that they were a paraboloid and did a calculation from that, and that calculation led to that the eigenvalue should be not the minimum of W. The eigenfunction is bigger than the minimum of W, that's a lower bound, but it should be about 1 plus the dimension over 4 times the minimum. So in 1D, 1.25, in 2D, 1.5. And that's a predictor for the eigenvalues. You take the local minimums of the effective potential and multiply them by the 1 plus D over 4 fudge factor. Does that work? Well, what I'm showing you here is for that uniform 80 by 80 Anderson potential. I've plotted the first 100 eigenvalues. The ground state is about 3.7, going up to 100th eigenvalue at 5.7 or something like that. And then below it, I've done the heights of the local minima of W. And you see it does look like one is a multiple of the other. That's their ratio. And we were saying one is 1.5 times the other, and it stays very close to 1.5. So the heuristic did a pretty damn good job here. This is the Bernoulli potential. These things look pretty different. And this one, well, it stays to near 1.25. a while, for at least like 20 eigenvalues, then it's really more like 1.7. And even in the beginning, it's a little off, so it's okay. Nothing to write home about. This one was even correlated, not IID, just to see what would happen. That worked. We tried different amplitudes, and I did some statistics. So those are the means of the standard deviations. And they basically say no matter what potential you choose, it's close to 1.5 in 2D, close to 1.25 in 1D. And then I made this picture. And this picture I'm glad I made. What I did is I did, let's start with one dimension, which is the blue case. So what I did is I computed the ground state eigenvalue, and I computed the corresponding minimum of the effective potential, and I plotted them. Minimum of effective potential, eigenvalue. And if the eigenvalue was really 1.25 times the minimum of the effective potential, this red dots, which are examples of what I just said, computing the eigenvalue and the minimum effective potential, would be a line of slope 1.25 through the origin. And I drew that line, the blue line, and indeed these dots pile up there. Those dots are different random realizations. So when you change the random realization, the eigenvalue can change quite a lot, but W min changes too, and the ratio stays about 1.25. And then I did it not only for the first eigenvalue, but also for the 10th and the 25th. I did 50 runs for all each of them. Everything lines up pretty close to this blue line. Then I did it again for 2D, and then the line has slope 1.5, and 3D, the line has a slope 1.75. It seems to work. So this was in our paper, it was Science Journal of Scientific Computing paper, and it got picked up by a physicist named Wienerker, who presented it to something called the Condensed Matter Journal Reading Club or something like that. The Journal Club for Condensed Matter Physics, a monthly selection of interesting papers by distinguished correspondents. And I guess Wienerker is the distinguished correspondent. And he said, he wrote a little review of this, and he pointed to that picture in particular and said, to appreciate how astonishing this is, imagine someone telling you of a new method to find the eigenvalues of a large random matrix. Invert the matrix, sum the rows to obtain a column vector, that's invert H, and multiply it by all ones, sum the rows. Then search for local minimum in the reciprocal elements. This sounds like a crazy method, but figure 2 shows it works for localized eigenfunctions. So I thought that was cool, and since that time we've come to know Wienerker, and he's come to our meetings, and he's a great physicist. Okay, and let me finish up quickly then. So we've gotten some approach to the eigenvalues and some approach to the eigenvectors. The last thing I want to do is look at the eigenvalues, not just the first 10 or 20 or 25, but the whole spectrum of eigenvalues. The physicists often talk about the density of states, which is the sum of delta functions, one at each eigenvector. And so what if we try to compute density of states using our landscape? Well, the density of states is always computed by Weyl's law. That's the famous, the most important object in spectral theory, I guess, in spectral geometry. It says the number of eigenvalues less than some level E is, well, for Schrödinger, it says the number of eigenvalues less than E is a constant times the volume in phase space of the symbol of the Hamiltonian, zeta squared for the Laplacian plus V. And you look where that is less than E, and that volume in phase space tells you roughly how many eigenvalues are less than E. And that's correct asymptotically as E goes to infinity. And that's what Weyl proved in the beginning of the century for the Laplacian. And he also made a conjecture of the next term in the asymptotic expansion. And this is a test of Weyl's law. The black line, and this is done for the Anderson type potential in 1D. The black one is the n of E function. So it jumps up by 1 every time it hits an eigenvalue on the x-axis. And so it means that there are 160 eigenvalues between 0 and 1.4 or so. And the green is Weyl's law formula for the same thing. And what you see is it's lousy. The first eigenvalue is really about 0.3, and it starts off at 0 and moves up. And then it gets good for a little while because it crosses the curve and goes too far. But then it gets good up here. And of course, that's what it was about. It was about asymptotic as z goes to infinity. Nobody said it's supposed to be good down here. That's just a blow up of that. But now, I'm going to change it. I will change z with w. Just brutally. I won't even change the zeta squared. I'll just leave that. And to me, it's remarkable. This is done very well down here, picking up, right where the first eigenvalue appears, and does pretty well here in a matter of 10% or so error, follows along, and then seems to have the same asymptotics. And here's a blow up right near the beginning. This is actually quite important because this way that the spectrum takes off for the x-axis is very different if you have a random potential than, say, the Laplacian. For the Laplacian, it would take off transversely. And that takeoff is called the Lipschitz tail, or the Urbach tail, and it's something that physicists want to know. It's an important characteristic. This is some other examples. This is a personal favorite. The Weyl's law doesn't care where the ones and zeros are, they only care how many ones and how many zeros. So it gives you the same answer, Weyl's law, for this periodic potential as for this Bernoulli potential. The Weyl's law will give you these two parabolas on their sides. But the real spectrum is very different in these two cases. One looks like this, and one looks like, as I told you, transverse. And the effective Weyl's law using W gives you the orange line, and it works for both of them, while the other obviously couldn't. And this is the last numerics I'll show you. Here, this we looked at a one-dimensional potential made of 500,000 random numbers. We computed the first 7,000 eigenvalues and made a histogram. And here's the histogram. This is this Urbach tail I'm telling you about, where it goes in exponentially and flattens out. And they want to know about that. And even 7,000 eigenvalues is really not enough to see them. And even though this was a 1D problem, if you want 7,000 eigenvalues with 500,000 pieces in the potential, that took 40 CPU hours. And then we did it again using the effective Weyl's law, and we got this picture for the minimum of 1 plus d over 4, 1.25, times the minimum of 1 over u. And we get this picture, the green one, and that took 5 minutes. That one you can do on a laptop. And if you compare the two, they're certainly fairly close. And finally, I'll end up with a real application, just very quickly. This is that guy, the third one over is Shuji Nakamura, who's a consultant at our grant. He and these other two gentlemen got the Nobel Prize a few years back for the blue LED. If you want to make white light out of LEDs, you need a blue LED, a red LED, and a green LED. Now they also put amber in there. They said at the time that the LED lamp holds great promise for improving the quality of life for billions of people. And then there was a study in 2019 by the DOE that said if done right, we could have a 50% increase of efficiency in lighting from 217 to 235 by switching to LED-based lighting. That would create an annual energy savings more than closing down 92,000 megawatt power plants, and would save 890 billion in that period. So there are many challenges that have to be overcome to achieve what the DOE is looking for. And one of them is this one. If you look at different LEDs in different frequency ranges, you find this is mapping efficiency versus wavelength. You find the red LEDs and the blue LEDs that Shuji invented are quite efficient, but the green LEDs suck relatively, and that even has a name. It's called the green gap. And they've been trying to fix the green gap. And in particular, Jim Speck in our group, his group is very focused on this. And what they decided to do is look at what's going on at a quantum level using the landscape theory as their numerical method to do 3D calculations they couldn't do otherwise. And this is the first paper of what will be several in that direction. A 3D simulation comparison of carrier transfer in green and blue multi-quantum well nitride light LEDs. All these people were on that picture of our participants. Claude Weisbrook and Jim Speck are two of the PIs, and Yuren Wu is an affiliated scientist, and Cheyenne Linsky and Guillaume Leroux are students. And what they came up with was a way to design the green LEDs that already gets rid of 33% of the green gap. So this is huge, actually. And so I'll end there. The primary take-home message is this landscape function, or effective potential. It's easy to compute, but it contains an astonishing amount of quantitative deterministic information about the spectrum of disordered Schrödinger operators. And the other takeaway message I would say is, wouldn't it be nice to prove these things instead of constantly saying, well, this picture looks pretty much like that picture. And most of these things I don't even know how to formulate a conjecture rigorously, having thought about it for quite a while. So there's a lot to be done there. And I will stop there. Oh, I put up some more references. You can get them on my website. Okay, thank you very much.